So here we go, proving theorem 63.1. And this one is the essence of composition. So this is probably the most important theorem of the lecture. And this is the main thing you'll be using when you use composition. Typically people are going to be using composition in a context where you're talking about functions. So let's look at what this is telling us. It's saying if you have two functions, f and g, then their composite is a function. Okay, so that's something we're about to prove. And also, if you try to evaluate that function at any point x in the domain, then you get this. So if you remember, function evaluation is like inputs and outputs. Functions are sets of pairs, but they establish these input-output associations. So what this is saying is, if you take anything from the domain and take it as an input, and then you try to see what's the output for the composite, then the output that you'll get is what you would get if you first fed that input into f and got an output, and then if you feed the result there into g and then get an output. So it's kind of like if you think of a function as like a machine, like if this is f and it's a machine that you input things into, like x, and things come out, like f of x. And if you think of g, like a machine that you can input things into, and then g of those things comes out, then the composition is basically what you would get when you mush these two machines together and connect a pipe here, the outputs of f to the inputs of g. Then you get an overall machine, which you can stick a box around and hide the internal mechanisms if you want to. And you have an overall machine with an input pipe here, you stick something in, and something comes out. And what comes out will be, what comes out, according to this, will be what you could call g composed with f at x. So this is sort of telling you that if you mush the f machine into the g machine like this, with this one on the left and that one on the right, connecting the pipe specifically from the output of f to the input of g, then that is the machine you're creating when you create g composed with f. Okay, and I hope this picture sort of reminds you of how when we were looking at these things, which are not both functions, in this example, t was not a function, but if it were, then the composition, the idea still applies, that when you're forming the composition, you're sort of taking this picture and this picture and then mushing them together like this, and then seeing what paths exist from the left to the right. And when you're talking about functions, which t is not one here, but if you were talking about functions, then you can follow an input from the left to the right, where it becomes an output. All right, let's prove this thing. So this is an if-then. Assume f and g are functions, then 1 holds and 2 holds. So I need to start by assuming that f and g are functions. Then I need to prove a couple of things. So let's focus on number 1. I need to prove that g composed with f is a function. So let me go and look up the definition of function to remind myself. There are two things to prove. That I'm looking at a set of pairs, so I need to prove that this is a set of pairs, and also this. Okay, the set of pairs part is easy, because if you look back at the definition of composition, anytime you compose two things, you're going to get a set of pairs. In fact, even if the things you started with were not sets of pairs, when you compose, you get a set of pairs. So that's just from the definition. If I strictly follow the definition of being a set of pairs, then probably there's a lot of talking involved in trying to show how this definition leads to technically, formally, that I'm looking at a set of pairs. But I'm going to skip it just because it's not the most important thing to focus on, but one could fill in those details. So I'm going to say by definition 60 by the definition of composition, G composed with F is a set of pairs. All right, great. Now for the actually important part to focus on, which is this. So this is a for all. So I'm going to have to use a universal generalization kind of argument to prove this. So now consider any xy, xz in G composed with F. And then my goal is to show that y equals z. So my goal is to show y equals z. So these are elements of a composite, so this is something that I can unpack. This implies that there is a middleman, right? These are two membership statements, actually. This is in G composed with F, and this is in G composed with F. So for each one, I can get a middleman. So we can get a, let's call it U, such that xu is in F, and uy is in G. So that's me using the membership of this in the composite. We can also use the membership of this in the composite, and that'll be a separate existential instantiation. So we can also get a middleman for that. We can get a, but I can't use the same variable, right? That would be a mistake. We can get a v such that xv is in F and the pair vy is in G. So now remember, my goal was to prove that y equals z. Somehow the function hood of G composed with F is probably going to follow from the function hood of F and G individually, right? So if I can see a chance to use the fact that F and G are functions, then I should take that chance. And here's a wonderful chance to use that F is a function, right? Since F is a function, and the pairs xu and xv are both in F, we have u equals v. All right, so since u equals v, now can I use the fact that g is a function? So you cannot use g's function hood directly on these facts because the first positions don't match, but we just found that they do in fact match. So thus, let's see, let me just switch the v to a u here. U comma y is in G. So this is like axiom 2, right? I'm taking this statement and then replacing the v by something that I know v is equal to. So u comma y is in G. Now since G is a function, and uy just realized that, okay, so I made a typo, which you may have noticed. So in this line, this was an existential instantiation that used the membership of this pair in this composite, right? And then I meant to make the second line, this one, be an existential instantiation that uses the membership of this pair in this composite. But I put a y here rather than a z. I meant to put a z here. So right now, this v is achieving nothing more than what the u achieved. This is totally useless. So let me go ahead and fix that. So right here, this was meant to be a z. That's what's so useful about v. Otherwise, it's really not adding any information, right? So then, yeah, then this also was a v. Yeah, so we do actually have uy and wait, no, z. This also was a z, sorry. So we have VZ and UZ. We have UY and UZ in G. Okay, so UY, UZ. So since G is a function, UZ is in G and UY is in G. We have Y equals Z, which was the goal from the very beginning. So we considered any of these things in the composite, and we got Y equals Z. So thus, G composed with F is a function. All right, so that's the proof of part 1 here. Now let's prove part 2. So I'm going to start with consider any, because here I'm proving a universal. Let me put it in visibility. So here I'm proving a universal, this. Let me actually copy it down there so you can see it. Okay. Good to announce what we're doing. We will now prove this. So now consider any x in the domain of G composed with F. Now I need to make some statements about evaluations, right? So my goal is now to prove this. So I need to make statements about functions of inputs, right, with inputs fed into them. So what will I use? Probably essence of evaluation, right? So the most useful aspect of this, I guess, is part 3 here. So let me reframe my goal in terms of thinking about y equals f of x, thinking about it instead as pair x, y, and f. That's what Theorem 51 Part 3 enables. So right now, to start with, my goal looks like it's proving that when I take this function, which we now know is a function thanks to work up here, my goal is to show that when I take this function and feed in x, I get this stuff. So let me represent this stuff by a bunch of blue scribbles. That stuff, the thing I underlined in blue. So that's my goal, right? By Theorem 51, was it? Yeah, Theorem 51 Part 3, since this is a function and x is in its domain, my goal is actually equivalent to showing that the pair x comma blue stuff is in this function. So actually my goal is showing x comma blue stuff is in there. So that's really my goal. Okay, and actually let me fill in what the blue stuff is. It's this. This is my goal. So I'm trying to show that a certain thing is a member of a certain composite, right? And I know how to do that. To show that a pair is an element of a composite, I need to find a middleman. So I need to find something so that x comma that thing is in F, and that thing comma this is in G, right? So I want a, let's make it red scribble, such that I want to find a red scribble such that x comma that thing, that red scribble, is in F, and the red scribble comma g of f of x, this, is in G. That's what it takes to get this pair to be in this composition. Okay, so any ideas for what a good candidate for the red scribble should be? Remember, f is a function. So what do you think is going to fit here? There's only one thing that fits here, and it has a very special name. What must the red scribble be? it can be none other than f of x, right? F of x is that which fits here in a pair with x there, such that the pair is an element of f. Okay, so we think we found our red scribble. Now, I keep talking about f of x, but can I? Right? Like, can I talk about f of x? Usually we're only allowed to talk about evaluations when we know that the thing is in the domain of the function. So I'm totally okay talking about g composed with f of x because I've assumed x is in the domain of that composition, right? But is x in the domain of f? Is it? So let's go ahead and unpack this. Sorry, x is in the domain of this thing, right? So there is some, let's call it z, such that x comma z, the pair is in there. That's from the definition of domain, the existential instantiation that it allows us to do. Actually, usually the language we use is we can get z such that this is true, right? But this language is also fine. This sometimes this language looks misleading. It looks like it has the z being bound under the existential quantifier there is. But people will use this. Okay, but I want to be better than that for now. We can get z such that. Yeah, but you will definitely see people just write there is a z such that this is true, and they'll assume that they've already gotten that z, so it's not really bound anymore. Okay, anyway, this is in the composite. This can be unpacked, right? So that means there exists a middleman. So we can get, or there is a middleman, let's call it y, such that that's in f, and this is in g. Then, okay, so the pair xy is in f. That tells me x is in the domain of f. So suddenly it's definitely valid to talk about f of x. But also, I think I can directly use this. If a pair is in f, then the second position is f of the first position. This works whenever f is a function, which it is a function here, right? That was assumed up here in the first line of the proof. It allows me to assume that. So then, since f is a function, by theorem 51.2, the second position is f of the first position. Y is f of x. So then this pair is actually f of x, that's what y is, comma z. And that's what's in g. So I'm basically applying axiom 2 to this statement, replacing y by something that it's equal to. Okay, but g is a function, right? Since g is a function, again, by theorem 51.2, the second thing is g of the first thing. Z is g of f of x. Right? So now I know what z is, so look what I've got. X comma g of f of x is in the composite. So I actually achieved this. Interesting that I got it just from unpacking things. I didn't actually have to pursue this part so actively. So now I'm referencing this here. So since that was a while ago, so let me remind the reader about it. Since the pair x comma z is in g composed with f, we have, now I'm using axiom 2, replace z by something it's equal to. And the reason that was our goal was because, again, theorem 51 tells us that that's what it takes. Theorem 51 part 3, I guess, tells us that that's what it takes to get, well, I guess part 2, well, part 3 also, but let's just reference part 2 to be more specific. That tells us that that's what it takes to get G composed with f of x to equal this thing. So by theorem 51.2, again, so it's the third time we use it here, since G composed with f is a function, the second thing here is G composed with f applied to the first thing. And there we have it. That's what we needed to prove, right? This. And that's proven. So when the things that you're composing are functions, this is telling you when the things that you're composing are functions, then you have a really nice way to talk about evaluate what is the evaluation of the composite at a particular input. You don't have to work with the annoying definition of composite here. No, don't touch this. Instead, if what you're composing are functions, go right ahead and evaluate using this principle here. So here's theorem 63.2. This is the other part of essence of composition, part 2 here. It says if you have f mapping x to y and g mapping y to z, which I like to depict in this form, which is kind of more visual. F takes you from x to y, g from y to z. Then the composite, which is written in this annoyingly backwards looking way, G composed with f, takes you from the beginning all the way to the end. So let's prove this one. So assume f maps x to y and g maps y to z. Then what do I have to prove here? 3 things. So we must prove, all right, I've written it out here. We have to prove that G composed with f is a function. So I'm just spelling out what is the mapping notation here saying. It says these 3 things. G composed with f is a function, x is the domain, y contains the range as a subset. Okay, I kind of wrote this backwards with a backwards subset symbol. The range of G composed with f is a subset of y. So these are the 3 things that we have to prove. So let's just write them separately. Proof of 1. Oh, well that's actually, if f and g are functions, then the composite is a function. That was part of what we just did, right? So that's just theorem 63.1, the one we just did. So that's done. Okay, proof of 2. Let's do that one last. Proof of 3. So the range of G composed with f well, that's actually a subset of the range of G, right? That's by this. This is true even if you're not looking at functions necessarily. So by theorem 62.2. So since the range of G is a subset of y, a subset of z, what? Okay, I need to prove this, right? So I need to prove that this is a function, its domain is x, and its range is a subset of z, not y. This is a typo. Or an error, a mistake, not a typo. Okay, so this is really what I want to prove. Okay, so since the range of G is a subset of z, that is part of what is meant when we say G maps y to z, right? That the range of G is a subset of z. Then we have, by the transitivity of inclusion, that the range of G composed with f is a subset of z. So that's the proof of 3. Now for the proof of 2. So that one is the most interesting. Let me get this stuff kind of off to the side and give this one the most room. So x is the domain of f, right? That's coming from this. X is just another name for the domain of f. So what we must prove is that the domain of G composed with f equals the domain of f. Right? But if you look back here, this is why we cared about this assumption that gets us equality. If you want the domain of a composite to equal the domain of the sort of first thing in the composite, the right-hand thing, if you want this equality, then you need this to hold. So we need the range of the right thing to be a subset of the domain of the left thing. So by theorem 62.1, we are done if we can show that the range of the right thing is a subset of the domain of the left thing. If we can show that the range of f is a subset of the domain of G. Okay, but we do have this, so here's how we have it. The range of f is a subset of y, right? That's because of this mapping statement, or we assumed it here, right? This assumes the range of f is a subset of y, but y equals the domain of G because of our assumption here. And so we're done. The range of f is a subset of the domain of G. So you see how getting to this conclusion required that the y that shows up here is the same as the y that shows up here. You see, composing, because we needed this assumption in order to get this equality of domains, because of this, composing functions seems to work a lot more smoothly when the codomain for the one on the right equals the domain for the one on the left. So this kind of matches up with the picture that I was making here, where you have x, y, z, f is here, and g is here. And there's this one thing in the middle that matches. The codomain of f is the domain of G. That's the situation in which composition works the nicest. Then you get G composed with f maps x to z. Otherwise, if you don't have this, then you can still talk about G composed with f. Like part 1 here allows you to do it, right? Part 1 works, any two functions, you can compose them and you'll get something, right? But you won't get this nice mapping result where the domain of G composed with f is the same as the domain of f. Okay, so I will end the official important portions of lecture here, and the rest will be optional viewing if you want more details. One of the things I'll do in the optional viewing is show you an example where you can see why you don't get the domain of G composed with f being the same as the domain of f when you don't have the y's matching up here.